Okay, so first thing, exam 2 is a week from Thursday. So that is the 10th. And the topics will be all the stuff that we've covered so far. So up through entropy. And so today I'm going to go over that problem that I messed all up last time. Just get it right. Talk about what you do know about changing from rates to fixed amounts and that kind of stuff. And then I'm going to do a big outline of all the topics so far. I just feel like it's helpful. So we're just going to go back to the beginning, go back over all the equations, talk just briefly about each issue as it comes up. And then after that, so starting next time, we're going to get into actual power cycles and refrigeration cycles and analyzing the efficiency and the performance of actual cycles where we're actually describing the steps in the refrigeration and calculating the efficiency at each step and that kind of thing. Okay.
Yeah, going around the, what do you call it, PV diagram?
Yeah, I think we'll probably use temperature entropy most, okay. But it depends what you're looking for. Yeah.
What you're looking at.
Yeah. Okay, so here's the example that I brought up last time, and I tried to find a book where I took this example from, but I couldn't find it. So I'll just talk about what I know, and I'll just be careful this time. I was just sloppy about what the quantities were that we're dealing with. So, okay, we have a steady state turbine. And at the inlet, we have steam above the saturation temperature. The pressure is 30 bar. The temperature is 400 degrees Celsius. And the speed is 160 meters per second. And at the exit, it's a saturated vapor. The pressure is atmospheric pressure, 1.01 times 10 to the 5th pascals. Why do I have two things there?
Yeah, we don't need to know the temperature?
We can't.
Saturated?
Well, yeah, I mean, I guess I just gave you two that match up, but we don't need to know that. So the temperature is 100 Celsius because the pressure is atmospheric. And then the speed is 100 meters per second. Okay, so at the inlet, it's superheated vapor, so you need to know the pressure and the temperature to use the tables, and we have it. At the exit, it's saturated vapor, so you need one or the other, and we have it. We're given that, so this is where it all started going off the rails. We're given that the rate of heat loss per rate of mass flow is equal to negative 22.6 times 10 to the third joules per kilogram. And the outer surface temperature is 350 Kelvin. And we want to know first what's sigma dot over m dot. So that's like a rate of entropy production that tells us something about the efficiency. And then second, what's rate of work done divided by the mass flow rate. So before I go into the calculations, this is the stuff related to what was going on last time. So this is steady state. And so we know that these flow rates are constant. So let's name this just random property X. Steady state means that this d property dt is constant. And so if you have a constant rate of flow or work done or whatever, then the fact that that's a constant means you can pull it out of the integral and you get that the change in that property is equal to the constant times the change in time. And so what this tells us is we can use all of these equations in a DDT format like we're used to, or we can also use it as a change of like total work done over a change, over an interval of time or whatever. So that's the first thing. So we could do that if instead we were given Q for the control volume divided by M is some amount. We could just assume that that's some interval of time and do the calculation that way. And then the second thing is the units. I think this is where I got sort of confused last time. So the units of Q for the control volume over m dot are equal to, so the rate of heat transfer is joules per second. The mass flow rate is kilograms per second. And so the seconds just cancel, and Q dot over m dot has the same units as Q over m. All right, so we're going to do this problem in terms of all these rates, and then like say that you get a value of, so say we get a value of W dot over M dot. Well, that's also, that would also give us W over M. It's the same thing since it's steady state. And because of that, then we could figure out if you want to know like how much actual work was done, you could do that based on how much mass flowed through. You could say, okay, like, so we know work per mass. So how much total work was done if 50 kilograms of fluid is flown through, and we can use that equation. All right. So the first thing we want to do is calculate this rate of entropy production. We know we're talking about a turbine, so we're going to use control volume entropy equation. So ds dt for the control volume is equal to all of the q dots over temperature at the boundary plus m dot times the specific entropy at the inlet minus m dot times the specific entropy at the exit plus sigma dot. I already changed the mi and me's to m's. And then steady state means this is 0. We're given the total rate of heat transfer per rate of mass flow. So we have 0 is equal to this. And let's divide everything by m dot. So I'm going to put the m dot in here. And plus SI minus SE plus sigma dot over m dot. And so now we can write this as 0 is equal to, we only have heat transfer at one temperature. I'm going to write this as Q dot over M dot divided by the temperature at the boundary plus SI minus SE plus sigma dot over M dot. And so 0 is equal to negative 22.6 over the temperature at the boundary, which was 350 K. Plus SI minus SE plus sigma dot over M dot. And now we can use the tables to look these up because for the superheated vapor, we have everything we need to look things up. And for the saturated vapor, we have everything we need. So SI is equal to 6.9212 times 10 to the third in SI units. And SE is 7.3549 times 10 to the third. So 0 is equal to, can one of you guys divide this out for me and plug this all in? I guess I'll rearrange this. So we got sigma dot over M dot is equal to 22.6. Oh, times 10 to the third. I left off at 10 to the third here. Over 350 minus 6.9212 times 10 to the third plus 7.3549 times 10 to the third.
got 498.3. That's what you got, Cole?
498.3. And that should be in joules per kilogram. Okay. And because this is steady state, this is the same thing as sigma over m. Okay, then part B. Now we're trying to figure out the rate of work over the mass flow rate. None of that stuff appears in the entropy equation, so we're going to have to use the control volume first law for this one. So ds dt for the control volume. Nope. dE dt is equal to q dot minus w dot plus m dot times the quantity hi plus vi squared over 2 plus gzi minus m dot times the quantity he plus ve squared over 2 plus gze. And it's steady state, so ADT goes away. Divide everything by m dot.
Wait, are we also doing away with the potential energy? The Zi and Ze?
Yeah. I guess I didn't say that, but with a turbine, you almost, I've never seen a case where you don't do that.
Yeah, unless your turbine for some reason angle upward.
Vertical. Yeah, exactly. Right.
Normally you draw your diagram just straight across.
Right. So yes, these, we'll assume those are 0. So 0 is equal to and I'm going to divide everything by m dot. So we have 0 is equal to q dot over m dot minus w dot over m dot plus hi minus he plus vi squared over 2 minus ve squared over 2. And yeah, that's right. So we already have q dot over m dot. That was given, so negative 22.6 times 10 to the third. And then minus the thing that we're trying to find. And now the enthalpies that we already looked up. So hi is, oh no, we didn't look those up, but we have to look them up. So hi is 3230.9 times 10 to the third. He is 2676.1 times 10 to the third. And then we have the speeds, so we can calculate the last two terms. Vi is 160, so 160 squared over 2. And V exit is 100, so minus 100 squared over 2. And so work for the control volume divided by the mass flow rate is 540 times 10 to the third, and this is joules per kilogram. Okay, and this is equal to work over mass in the steady state case. So then if you wanted to, calculate how much work is done by 50 kilograms, no, I'm not doing 50. Let's do 100 kilograms of mass flow. Work over mass is 540 times 10 to the third. So the work is 540 times 10 to the third times 100 kilograms. So 540 times 10 to the fifth. Any questions about that? Okay, that's the end of the second law and entropy. So now let's go through an outline of the topics so far. And I'll try to get all the key equations in here. Okay, so the first thing we did was sort of an introduction. We talked about pressure. And the pressure equation was that the pressure at the lower height minus the pressure at the higher height is equal to the density of the fluid times G times the height. We use that to talk about how to make barometers and manometers. Then we talked about work. And the most important one to us has always been the work of expansion and contraction. And the equation for that under any circumstances is work is equal to the integral from state 1 to state 2 of P dV. And this equation satisfies the first law sign convention. So you can just use this directly in first law problems. Remember to integrate to do this calculation. You need pressure as a function of volume. The most common way for that to come up is just for pressure to be constant. And then the other types of work are rotating shafts, electric power into the system, and electric power generated by the system. So then the second section was the first law of thermodynamics. We started out just with closed systems. So first law for closed systems. So the equation is that the change in energy is equal to Q minus W. And this is where we introduce that sign convention that we've pretty much used all the time with a couple of exceptions. Q is heat added to the system. W is work done by the system. And the change in energy is the change in internal energy plus the change in kinetic energy plus the change in potential energy. And these two often can be ignored. There are two simplifications. So I guess part B, let's call that simplifications for this. The first one is steady state. And the second one is a cycle. And in both of these cases, the simplification means that the change in energy is zero. Then we talked about the differential form of the first law. So that is dE dt is equal to Q dot minus W dot. The simplifications for this one. So if it's steady state, then dE dt is equal to 0. And Q dot and W dot are constant. Then part D, we're still on the first law for closed systems only. Then we talk about heat transfer. And as I go through these, just remember the sign convention for heat transfer, for the heat transfer equations. Can't be trusted for the first law. You have to come up with the signs on your own. The equations are, so number 1 underneath part D, conduction. That's called Fourier's law. And it says that Q dot is equal to negative kappa times A times D temperature dx, where that kappa is the coefficient of thermal expansion for a specific material. Not thermal expansion, coefficient of, that is what I have written here, but that's not right. It's the coefficient of, let's just call it conduction. I don't remember what it's called. If it's a linear temperature gradient, that's what every example has been that we've done. Then you can treat this equation as Q dot is equal to negative kappa times A times the change in temperature over the change in X. So that linear temperature gradient, like if you don't know any better, you just sort of assume that, and then you can just do it as a difference equation. You know the temperatures of the two sides, and you know the thickness of the material.
Yeah, because kappa and the area is not changing as a function of temperature or X.
Right, right. And then the second one is radiation. This is the Stefan-Boltzmann equation. And there are two forms of this one. There is the equation just for the radiation emitted by a body, which isn't usually too useful because you need to know the net energy absorption emission. And then there's one that's not as general, but if you have a smaller body surrounded by a bigger body, then you get the net radiation, and that's the one that you can actually use, like in the first law. So part A, the first one of these is totally general. This is the radiation emitted from a body. But it doesn't say anything about the energy coming into the body. This says Q dot sub E for emitted is equal to epsilon times sigma times A times T to the fourth. This epsilon is called the emissivity. And it's just a number that ranges from 0 to 1. Sigma is the Stefan-Boltzmann constant. A is the surface area of the body. And T is the absolute temperature. So I'll just say temperature in Kelvin. Although you could also do it in Rankine, but we haven't done that at all. And then the one that's more useful but not as general, B, is the net radiation emitted from a small body surrounded by a large body. And that equation looks similar. Q dot sub E is equal to epsilon times sigma times the surface area. That's the surface area of the smaller body times the quantity temperature of the body to the fourth minus temperature of the surroundings to the fourth. This area is the surface area of the smaller body. And then after radiation, the only one left is convection. This is more a curve fit than a law of physics. You just kind of throw everything into this one constant H, but Q dot sub E is equal to this constant H that you have to find experimentally times A times the quantity temperature of the body minus temperature of the fluid that's moving past. This H is an experimental constant. And this A is not the surface area of the body, but it's the area that's exposed to the fluid. Area of the body that's exposed to the fluid. So if the fluid is just flowing over the top of something, then it's just the area of the top. The area underneath doesn't matter.
Yeah, I think what mixed me up the first time with that, so with that catch-all term, when it includes radiation, it just, that T to the fourth dependency of radiation just doesn't matter in comparison to everything else. If you're just, like you said, trying to fit it with convection curves, so you don't have to worry about that T to the fourth.
Yeah, that's right. Or the it incorporates the conduction too.
Yeah, the conduction too, which has a bigger effect than I assume the radiation does.
Yeah.
So you don't have to worry about a T to the fourth.
Okay, so that was all about the first law of thermodynamics for closed systems, and now we're on to big category number 3. And that is material property relationships. So A is the PVT surface. And remember, I showed you 2 of these. One, they're just sort of qualitative. They're different for every substance. But there's one for materials that contract as they freeze. That's almost everything. And then there's a different one, just one little change that you see when something expands when it freezes, and water is the only one of those I know of.
I know where the curve thing goes backwards.
Yeah, right. And we talked about quality. So this was getting ready to start using tables. So quality for materials at saturation. So the quality is this lowercase x, and its definition is the mass in a vapor phase divided by the total mass. So you can write that as divided by m vapor plus m liquid. And so this has to be a number between 0 and 1. And 0 means all liquid. And 1 means all vapor. And you can think about that, the quality telling you something about how much energy you have stored in that material. At a certain pressure and temperature, you can't store any less energy than 0 quality. And at that same temperature and pressure, you can't store any more energy in that material than 1. And then with that quality, you can use that to calculate. So you can use X to calculate specific volume, any of these things in the table, any of these properties. Well, you can use it for any property, but I'm just going to list the ones that are in the table. So specific volume specific internal energy, specific enthalpy, specific entropy, and you do it as Q, so that's our stand-in for a general property, is equal to X times that property for the saturated vapor plus the quantity 1 minus X times that property for the saturated liquid. And then we defined enthalpy. And the enthalpy is equal to the internal energy plus pressure times the volume. And if you divide everything by mass, you can get the specific enthalpy, which also is the specific internal energy plus P times the specific volume. And then D, the specific heat. So there are two of these. CV is the partial of the specific internal energy with respect to temperature, calculated at a constant volume. And then CP is the partial of specific enthalpy with respect to temperature, calculated at constant pressure. And we're going to see that those are most useful to us in cases where the enthalpy and the internal energy are dependent only on temperature. So we can write these as total derivatives, and then we can, integrate them. And then E, then we talked about the two simplified material models. I guess I have 4 here. Okay, so simplified material models. So the first two are incompressible and ideal gases. So first, incompressible. You would use this for liquids and solids. And remember when we did the calculation where we had like a lump of some solid that was in a bath of water and they came to the same temperature and we calculated the change in entropy. This is the model that we used for that. This incompressible model means that specific volume is constant. Before the calculation, you just look that up for somewhere in your temperature range. And then the specific internal energy is only a function of temperature. And you don't have to worry about CP and CV. they're both just equal to 1c, and that's just equal to du dt. And so the thing about that is that you can separate variables, integrate, and you get that the change in specific internal energy is equal to C times the change in temperature. So that's a nice, simple, really useful case. If you can treat something as incompressible, that's a really nice, you have a lot of calculation strength there. Number 2 is ideal gases. That's defined by P times specific volume is equal to RT. And that R is not universal. That's for the specific gas that you're dealing with. And R is equal to the universal gas constant, R bar, divided by the molar mass of the material. And then for ideal gases, the specific internal energy is only a function of temperature. The specific enthalpy is U plus, PV is equal to RT, so H is equal to U plus RT. So that's also just a function of temperature. CP and CV are different. CV is just equal to dUd temperature. But from the definition of H, you can take that derivative and see that CP is equal to CV plus R. Since everything in this class basically has to do with the transition between liquids and gases, lots of useful engineering has to do with the transition between liquid and gas. Those two simplified models are really useful. It comes up all the time. Okay, number 3, we didn't talk about this much. There were a couple of problems that we did like this, but polytropic processes. And these are the ones where pressure times volume to some exponent R is a constant. And that means that you can write pressure as a function of volume. And so P of V is equal to C times V to the minus R. And because of that, in order to integrate the work of expansion integral, we needed to have pressure as a function of volume. This means we can do it. So work then is equal to the integral from state 1 to state 2 of C times V to the minus R dV. And then number 4, the last one in this category, is the tables. And the main thing to remember about these is for compressed liquids and superheated vapors, you need 2 properties to specify a state. And the way the tables are set up, that means that you have to look it up by pressure and temperature. If you're at saturation, you only need 1 property to specify the state. And so then you can look up any property you want by pressure or temperature. You only need 1. We do a lot of examples where the pressure and temperature you're given are in the table, but in a real problem, you pretty much always have to interpolate. So I just have this still under the same category of tables. So to interpolate, linear interpolation, f of x is equal to f at x1 plus f at x2 minus f at x1 divided by x2 minus x1. And then that fraction is multiplied by x minus x1. And the meaning of all this stuff is where x is the known property and f is the desired property. At saturation, you only need to interpolate once because you only have 1 independent variable. If you're not at saturation, away from saturation, then you have to do it in 3 steps. Calculate f at x, y1. Calculate f at x, y2. And then calculate f at xy. where this time X and Y are the known properties. And F is the desired property. Okay, so this was all under material property relationships. And now we're going back to the first law. Like chapter 4 is control volumes. Part A is the mass balance. So that says dm dt for the control volume is equal to mi dot minus me dot. One thing that's useful for this a lot, number one, is that the mass flow rate at either the inlet or the exit is equal to A times the specific volume, A times the speed of the fluid divided by the specific volume. And you can also write that. That's the most useful because specific volume is in the table, but you can also write it as A, the area of the aperture, times the density times the speed of the fluid. If you look at the speed of a fluid as it goes through an opening, there's actually a big difference in the speeds as you go around the area. If you track the fluid that's right at the edge of the boundary, it's moving really slow, and then the stuff in the middle is moving really fast. But this is the average speed. And then 2, in steady state, dm dt for the control volume is equal to 0. And so if you set dm dt equal to 0 in the mass balance equation, you get that mi dot is equal to me dot is equal to m dot. So we haven't, most of the time, most problems, we don't really explicitly use the mass balance equation, but every time we do this, we're sort of implicitly using the mass balance equation to enforce a steady state. And then part B. So part A was the mass balance. Part B is the first law for control volumes. And this says dE dt is equal to Q dot minus W dot plus MI dot times the quantity HI plus VI squared over 2 plus GZI minus ME dot times the quantity HE plus VE squared over 2 plus GZE and then we use this to do calculations for a bunch of different devices. So first was nozzles and diffusers. They're the same, it's just a matter of whether the fluid is sort of running backwards or forwards through it. The common simplifications are steady state, fast flow, which means Q dot is 0. It's a rigid device. So that means that the work rate is 0. And then we assume that there's no important change in height. So change in GZ is 0. And so you come up with the same thing for both of them, but I'm going to write it two different ways. For a nozzle, you get HI minus HE is equal to 1/2 times the quantity VE squared minus VI squared. Where both of these two sides are positive. And then for a diffuser, these would, the way it's written there would be negative, so I'm going to write it as HE minus HI is equal to 1/2 times the quantity VI squared minus VE squared. And each of these is positive. Let's just get through these devices and then we'll be done for today, and then we'll keep it going next time. So next is turbines. That was number 1. Now we're on number 2. Common assumptions. Steady state. Negligible heat transfer. Negligible change in kinetic energy, even though there is always some that the speed always goes up as it goes through the turbine because of the change in pressure. but we'll ignore that. And then assume that the change in potential energy is 0. And so the most simplified form is that W dot for the control volume is equal to M dot times the quantity HI minus HE. And then the last category of these is compressors and pumps. Compressors are for gas, and pumps are for liquid. Both of these can be used to increase the pressure. And we'll see when we start talking about power cycles that you need to have a pump in order to get the low temperature liquid into the high temperature region where it can power the turbine. But pumps also you can use to change the height of the liquid. But if you're increasing pressure, then, so this is, for both of them, when you're increasing the pressure, the common assumptions are steady state, no heat transfer, no change in height, and no change in speed. And so you get a simplified form. W dot for the control volume is equal to M dot times the quantity HI minus HE. Both sides of this equation are negative. So work has to come in the form of electricity to increase the pressure as you get to the exit. And then this is the last thing. So these were using a pump or a compressor to increase the pressure. You can also use a pump to just change the height of a liquid. You know, to raise a liquid. Common assumptions. Are steady state, no heat transfer, no change in enthalpy, no change in speed, and if you use all those, you get a simplified form that the rate of work is equal to M dot times the quantity GZ I minus GZE. And again, in this case, both sides of the equation are negative. Whew. That was a lot.
Yeah.
Only one more day like this. Okay, any questions about any of that? I think as tedious as days like this are, I think it's helpful to go through it, and it'll be helpful to have it in front of you, I think. So anyways.
I don't remember.
Yeah, exactly. Yeah, right.
Yeah, I've been trying to get better about doing that.
Yeah.